So for asking questions, please use the Q&A designated panel and specify who the question is directed to. Here on the panel today are Professor Stephen Gould and Dr. Dylan Campbell from ANU, Stephen Diamond from Stanford, and Dr. Brandon Amos from Facebook AI Research. I'm Yizhak Ben-Shabat, and I'll be moderating this session. We will start by going around the room, the Zoom room, so the speakers can refresh your memory and very briefly go over their talk. Steve Gould, on to you.
Thanks, Citic, and welcome everyone. So yeah, I wanted to just recap, I guess, the three key ideas that I introduced in my presentation that will set the groundwork for the rest of the tutorial. And so the first, as you all know, is the idea of deep learning or end-to-end learning as or end-to-end learning models as a computation graph or data flow graph. So we typically talk about layers within a deep learning network, but more generally we can think of these things as nodes, and each node performs some operation on the data coming into that node and then produces some output. So it has this so-called forward evaluation function. And of course, we chain these nodes up into a graph and process data from the input to the output. Now, typically, what we want to do is we want to learn the parameters of these forward processing functions. And in order to do that, we have a loss function at the end of the graph, and we want to change that loss function, or we want to change the output of the graph to move that loss function in a particular direction to minimize that loss function. And so in order to do that, we need to know how to change the inputs and the parameters of a processing node to move the output in the direction that we'd like. And the way we do that is by backpropagation, by estimating gradients. So with deep declarative networks and with convex optimization layers, what we do, instead of having this forward processing function as an explicitly defined function, it's implicitly defined as the solution to an optimization problem. So the question then becomes, if we have the output of a node defined as the solution set to an optimization problem, how do we compute the gradients? How do we backpropagate through that optimization layer? And so the way we do that is by looking at the optimality conditions, which are defined as an implicit function between the inputs and the outputs of the layer. And we use the implicit function theorem to differentiate that optimality condition. And that's what allows us to backpropagate the gradients. The last key idea is this separation of the implementations of the forwards and the backwards function. So we can use any algorithm in the forward pass to perform the optimization, and a lot of methods, in fact, just unroll the optimization in the forward pass. But we don't need to backpropagate through that particular implementation. So we don't need to use automatic differentiation in the backward pass on that implementation. We can use a specific implementation of the gradient in the backward pass, and that's very, very powerful. So those are the three key ideas. The idea of neural networks as a computation graph, the idea of implicit differentiation on optimality conditions, and this idea of separating the implementations of the forward and backward pass, which allows us to use very, very powerful methods in the forward pass and still compute gradients in the backward pass. Okay, with that, I will hand over to my co-presenters to give a brief introduction to their components.
Yeah, so I guess we can go by the video order. So next up would be Dylan.
Thanks, Citic. So in the second video of the tutorial, I looked at a small subset of the applications of declarative layers that have been considered by the community so far. So the first set were variants on standard pooling operations, which are used in neural networks typically. And we include a look at robust pooling, which replaces average or max pooling with a pooling function that's insensitive to outliers, and rank pooling, which considers temporally sequential inputs and summarizes them without throwing away the temporal ordering information. I then look at a couple of projection examples, including projection onto L1 and L infinity spheres, and projection onto the transport polytope, which is useful for optimal transport problems such as matching and ordering and so on. And finally, I spend a bit of time looking at geometric model fitting algorithms used in computer vision specifically, giving an example of relative and absolute camera pose estimation using the 5-point algorithm and the P&P algorithm, respectively. So this is by no means a comprehensive list, and there's many more examples covered in Brandon's video on applications in differentiable convex optimization layers. And then in the third video, I ran through a Jupyter Notebook tutorial on the DDN code base, which you're all welcome to try out and can be found at deepdeclarativenetworks.com. And the direct link is in the resources section at the bottom of the tutorial webpage. So in this video, I look at 3 examples, including a variety of possibilities for declarative layers, including a constrained Kale divergence loss layer, a robust pooling layer, and a perspective endpoint layer. So the notebook shows how to define these declarative layers in a training loop. And the layers are standard PyTorch layers that can be included in an end-to-end learning framework in the usual way. Okay, thanks.
Okay, thank you, Dylan. Yeah, next up is Stephen Diamond.
Thanks, Yizhak. So in my video, I talked about this work on CVX PI Layers that I did with Brandon and Akshay and others. And the idea here is to really focus on deep differentiable layers, which represent convex optimization problems. And this is a particularly interesting class of problems that have been studied extensively, but can capture quite a wide variety of different modeling situations. And also where we have a lot of interesting modeling tools for allowing users essentially to write down their optimization problem, their convex optimization problem in a natural way. And then they get sort of compiled into the more complex form that the solver requires. And so it sort of is like a separation between the user's view of the problem and then the solver's view. And the idea was essentially to leverage all this and for this idea of creating these differentiable convex optimization layers. And so we were able to basically build on CVX PI this Python modeling software that we've worked on in the past, so that a CVX PI problem can be turned into a differentiable PyTorch or TensorFlow layer. And there's different insights and breakthroughs that went into that. For example, work on how to sort of how exactly to handle differentiating through a convex optimization problem. It's essentially, as Steve Gould described, looking at the optimality conditions, but there's some tricky parts. But putting all these pieces together, you get this software CVX PI Layers, where you can just describe a convex optimization problem, and suddenly that can just be a node in your network.
Okay, thank you, Stephen. Moving now to the next speaker on the video, that would be Dr. Brandon Amos.
Hello. Yes, in my part of this tutorial, I guess I'm starting with the high level kind of vision and kind of setup that that Stephen Gould and Stephen Diamond have kind of laid, where we have this idea of being able to have differentiable optimization problems or differentiable layers by using the implicit function theorem and by providing this nice kind of interface and toolkit. And from a practitioner's perspective of wanting to use convex optimization layers, a lot of the tooling and software is out there. You can download our code, and it provides a really nice interface on, as Stephen said, on top of a lot of things going on underneath of the hood. And in my part of this tutorial, I very briefly talk about some of the implementation considerations that you might want to think about if you end up having to kind of like go deeper into the implementation, or if you start using our implementations and you find that it's not running as fast as you want it to, or you really want to squeeze the performance of these. And the kind of implementation considerations come up because of the peculiarity of the modules that we're using, and the kinds of computations that are happening in both the forwards and backwards pass. And there are a lot of decisions that are really not clear that we have to make when handling these operations at kind of like the general level of say convex optimization problems. So I'll briefly talk about that on the forwards pass and the backwards pass of doing the implicit differentiation. And then I kind of come up on one level and talk about some of the other applications, I guess, in addition to the ones that Dylan has mentioned in his video. Kind of focusing on two applications in the controls setting and in data poisoning. Yes, that's it for my part of this tutorial. Thanks.
Thank you, Brandon. Moving on to Akshay.
Hi. Yeah, so in the last part of the convex optimization layers tutorial, we walked through a notebook that highlights how to actually use convex optimization layers like in practice. And so in particular, we drop a CVX Pi problem down into PyTorch, and we train the parameters in it. And in particular, we show it's sort of complementary to the example that Brandon talked about, where he talks about control a little bit. We show how a convex optimization layer can be used for a structured prediction task, so a supervised learning task, but where the thing that you're trying to predict is like a high dimensional vector with a lot of structure. And we show how you can sort of, using the standard tools that are really familiar to machine learning practitioners like PyTorch and automatic differentiation, you can get a sort of a simple but still pretty sophisticated, convex optimization based model for structured prediction. And yeah, that's the third part of the talk.
Okay, thank you all for the brief overview. Now we can move on to start taking questions. So I want to encourage the audience to pop your questions into the Q&A section, and I will read them out to the speakers. So we already have a first question lined up. And the question is, it's not directed to anyone, but I guess it's the implementation part. So I guess we can start with Dylan, and then Akshay can also maybe pitch in. So the question is it possible to wrap a differentiable convex optimization layer into torch.nn.module so that we perform implicit propagation through this module, for example, when performing layer weight low rank reduction, and incorporate it into the torch NN module model? There are also follow-up questions. I'll read them out one by one. So I guess actually, Akshay, you can go first.
Sure. Yeah, so you can easily drop the CVX Pi layer into a torch.nn.module. It works like just any other PyTorch operation that's differentiable. So it can be used, anywhere that you can use a differentiable PyTorch operation in. So we don't have GPU support yet, then that's because the only solvers that we support so far are only implemented for the CPU. And we do sort of have an aspiration for eventually building, a PyTorch-based generic convex optimization cone solver. And once that's done, in principle, these problems could be solved on the GPU, but we don't have a concrete timeline as for when that would be done.
Okay, so the follow-up question, I think you kind of addressed it, is will GPU / multi-GPU training be available as well?
Yeah, so I guess, yeah, like I said, we haven't implemented it yet. We would love open source contributions if anyone has a sort of PyTorch generic solver. So I guess one nice thing about CVX Pi Layers is that its implementation is at least partially agnostic to the solver that's used. So we could in principle support additional solvers than the one that we, than the CPU based one that we support right now. Multi-GPU, that's a question. I think we would first need to get to a GPU, single GPU solver before we would think about multi-GPU. But it could be done in principle.
Dylan, you wanted to?
Yep. So we have a similar situation for the declarative nodes code base. So we do indeed wrap the nodes in torch.nn.modules, so you can use them as a standard layer. And this means that you can transfer data across to the GPU, transfer the problem across, and it will work in the way that you would expect as any other torch layer. The reason we can do this is because we're forcing the user to write the forward function. So unlike for CVX PI, you can't just have a solver that runs it once you specify the question. For the declarative layers approach, you have to specify the forward algorithm and write that out. So for example, in camera pose estimation, you'd write a PNP algorithm or load a library to do that. And so this means that you can write a parallelizable solver in native PyTorch if you like, and use a batch solve in that case. There is a slight downside with using batch solvers though, because for optimization problems, it would mean that you would need to wait until the like the worst element of the batch has finished solving. And so, you know, some of the problems might actually only take a few iterations, but you still need to run until the worst element in your batch has finished.
Thank you. And the final question within that question thread, will any bottleneck issues occur due to batch training? Dylan, you want to take that one first and then Akshay?
Sure. So it's set up to run in batch mode. I don't think there are any specific issues apart from the one I just mentioned, although I guess a sort of corollary of that is that when you do run a solver in batch mode, then you do run the risk of entangling the elements of your batch. Because if you don't run all of them to convergence, then there is some dependency between your batch elements, which might mean that your gradients are a little bit incorrect. But if you do run it to convergence, then that's fine. So a way to address this would be to perhaps use a group norm or something like that to be the termination condition for the solver. But in the absence of that, you just need to make sure that you actually have solved your problem before you compute the gradient.
Akshay, is it the same in the CVX PI layers?
Yeah, the situation is similar, where if you're solving a batch of problems, you're limited by convergence on sort of your, I guess, least well-conditioned problem. There's also some sort of multi-threading. We have like one open performance issue that will be addressed probably pretty soon. But yeah, so basically the situation is very similar, I think, to what it is in the deep declarative network case. So there's nothing necessarily fundamentally limiting about batching. We'll solve the problems in parallel. But because these operations are sort of more complicated than your average neural network operation, you may see a longer tail latency than you would expect.
Okay. Thank you. Well, I guess I have I'll take the next question. So this one goes to Steve Gould. And the question is, well, it's a very general one. When should we use deep declarative networks? Steve?
All right, thanks, Yizhak. It's a good question. So there are obviously some good things and some shortcomings of putting optimization embedding optimization within your deep learning model. I think Dylan and Brandon talked about why you might want to do this. So certain applications, there are problems that we already know how to solve. We don't have to learn the solution. We have a long history of research into how to solve particular problems. So in computer vision, there are problems like PNP solvers, in some of the control applications that Brandon talked about, and Akshay also mentioned structured prediction. And so there we have models that we know how to solve. We know the behavior of those models. We have guarantees on the outputs of those models, and we also have in many cases efficient algorithms for doing so. I guess the other side of the equation is the observation that Brandon's made in his OpNet paper. We also make in our Deep Declarative Network paper, in that optimization problems and deep declarative networks subsume traditional deep learning. So anything that you can express in a traditional deep learning model, you can also express within in a model that has embedded optimization within it. So just from a conceptual point of view, you can think of all networks as being these deep declarative networks, or networks with optimization embedded in them. Now, the reason you might not want to use optimization within your network is, first of all, if you don't really care about guarantees and the outputs of layers, so you're happy to approximate a particular operation by learning it, and you have real performance issues where you really need your network to be running as fast as possible. So it's going to be in an embedded system or something like that. These optimization algorithms are getting faster all the time. As Akshay mentioned, at some point we'll have GPU-enabled convex optimizers. And so, my view is always you should solve the problem that you care about first, and worry about speeding things up later on. So in short, if you know something about your problem, if you have a mathematical model or a physical model that you don't want to learn from data, that you want to guarantee the behavior of, then in that case, it makes sense to use deep declarative networks or differentiable convex optimization, and embed that within your end-to-end learning model, and learn the things that you don't necessarily know about. So the transformation of the features or the visual perception, and then the things that you do know how to solve, the modeling aspect of it, you embed as an optimization problem.
Okay, thank you, Steve. The next question goes to Stephen Diamond. What are examples of problems that cannot be transformed into a fine solver, a fine form?
Sure. So if anyone, for those who watched my video, one of the important choices we made in the design of this CVX PI Layers was this some limitations on the kinds of CVX PI problems that are permitted, and it's not very onerous. It's basically, the idea is that at the end of the day, we want to have, so what CVX PI basically is doing is it's taking like this problem as it was written down, which is, you can think of as sort of expression trees or something, right? It parses it. And then at the end, it's essentially outputting a bunch of matrices that get fed into the solver. And so our idea for how to basically, for use in a CVX PI, in a neural network kind of setting, or like a deep declarative network kind of setting, we didn't want it to be running through all those transformations like every time you run this forward pass, for example. And so essentially we structure things so that the mapping from parameters in the original problem into the this matrix that is output at the end is a linear mapping, or an affine mapping. And that's what we call it, affine solver, affine form, because if the CVX PI sort of just compiles it and then it's gone, and then you just have a matrix, you have the solver, you have another matrix to sort of get back from the solver's solutions to the original solution. And I think you can really, it's really not very limiting in that I think anything that you could, just sometimes you have to write things a little bit differently. So the biggest example is like, if you have a quadratic term, right, x transpose px, and where p is a parameter, that's going to be pretty natural, but unfortunately it doesn't really fit with this particular structure to have things set up that way. So you would need, for example, to have, p to the 1/2 in the matrix sense as your parameter, and then do like, px, p to the 1/2 times x, and all of that, like L2 norm squared. So instead of your parameter being this inner term of the quadratic p, it would be the matrix square root of that. So that's one example. But generally, yeah. So CVX Pi will tell you if you're not doing it right, and we have different examples online. But most problems will fit; it'll be fine. I think you also cannot multiply parameters together. Akshay, is that right?
That's correct. But you can handle that by introducing like slack variables. And then, so if you want to multiply two parameters together, you would introduce one variable and then add an equality constraint that variable is constrained to be equal to the parameter that you would want it to multiply by the other parameter. So I guess to add on or to reinforce what Stephen has said, that like in practice, when we've been using CVX Pi layers for a variety of applications, we've never not been able to express what we wanted to express in ASA form. You sometimes just need to add additional slack variables and constraints.
And I think this is a really nice outcome of the project, is this sort of pulling the modeler out, CVX Pi out, and it goes even further towards this idea that you don't need, you can have different solvers in there. The declarative, what you declare is one thing, but then how the forward pass is done, how the backward pass is done, these could be done in many different ways. And here even, the mapping from parameters to, like the mapping from the parameters into the solver form, this is also sort of really taken care of. Anyway, yeah, so CVX Pi is really getting out of the way here. And so it's kind of like an implementation detail on the one hand, but I think it's also super important.
Okay, thank you. I would like to remind those who joined a little bit late that you can pop your questions in the Q&A section down below, and we'll be taking them one by one. So the next question, I guess, would go to Brandon. What are examples of problems that, what are the advantages of the approach you take over an unrolled optimization approach?
Sure. I guess Stephen Gould mentioned this at the beginning of the tutorial, and I guess in his part of the tutorial as well, in that if you wanted to, you could compute the derivatives to optimization problems by unrolling through the solver. And in many cases, this will give you the right derivative, but it requires that you store all of the computations that happen along in the intermediate path. And if you're solving sufficiently high-dimensional convex optimization problems with a lot of constraints, this becomes very intractable just in terms of keeping this around in the memory and keeping all of the steps along the way. And it's also computationally not that great to have to perform in reverse mode all of the computations that led you to the solution to the optimization problem. So as an alternative that theoretically works and is significantly more efficient in terms of computation and memory is that if you do implicit differentiation, then you're able to do something that's like just looking at the last iterate. So you no longer have to save the entire chain of computations when unrolling the problem, or that you would have to if you unrolled the problem. And this works well in the convex setting, like with the differentiable cone programs and with CVX PI layers. I guess more generally in other non-convex optimization settings, it might be not as clear of a choice between deciding to unroll the solver or do something more analytic, because there might not be as nice of a set of optimality conditions that you can differentiate through. Yeah,
and
thanks.
One thing that I would also add on to what Brandon said, another advantage that we've seen, at least from an engineering perspective, for differentiating analytically for convex optimization problems, is that because we've decoupled the implementation of the derivative from the actual optimization algorithm, we can easily experiment with other solvers that also target convex the convex cone format. So for example, we initially only supported SCS, and I think maybe in our current release we only support SCS, which is a particular ADMM solver. But with very little work, we were also able to add experimental support for an interior point-based solver without having to implement that in PyTorch, for example, and unroll it. So we can take like hardened, well-tested solvers that were developed in the scientific programming community and that weren't developed in PyTorch. So there's no way to automatically differentiate through them, but we can still analytically differentiate through them because we can map them we can map their optimality conditions to ours. So that's another benefit we've seen in practice.
We've also noticed, particularly in cases where you need to do a significant number of iterations to converge, that the gradients from the unrolled optimizer often accumulate floating point errors. So you do get some degradation of the gradient in that way as well, which you don't get if you compute the analytic solution with implicit differentiation.
Okay, thank you. The next question goes to Dylan, I guess. Do I need to find the global optimum in every forward pass?
Okay, so I guess this refers to when you have non-convex objectives, because you don't get this situation with, obviously, with convex problems. So you don't, the theory works for any local optima or saddle point. So your gradient will be correct no matter which solution you get. But you do want to get a good solution because you want your gradients to be meaningful. So as you train, you want your network to converge towards getting the correct or a good solution most of the time. So while it's okay if sometimes you get poorer examples, poorer solutions, you want on average to get a good solution. So you don't need it to be the global optimum, but you want it to be a reasonable solution most of the time.
So I'll just add one thing to that, and that is that you need the optimality conditions to hold. So in solving either a convex problem or a non-convex problem, you need to make sure that you're close enough to either a local optimum or the global optimum so that the optimality conditions hold, and therefore your implicit the gradient you get from implicit differentiation is correct. Optima, you can come up with pathological examples where if in each forward pass you're picking a different local optimum, then your learning algorithm may get stuck or may bounce between different solutions. So you need to be a little bit careful that the algorithm that you're using in the forward pass to give you your solution is consistent, in that if you give the same data to the network a second time, it will find the same solution or a solution very close to that.
But if you do have an efficient global solver, then yeah, definitely use that. It will make your learning algorithm converge faster.
Okay, thank you. We have a question to Dylan in the chat. How long did it take to train the model for robust point cloud classification? What is the size of the data model that can be solved in adequate time with existing implementation?
So for the point cloud classification, there is very little overhead over just using the standard point net. So we were just adding a single robust layer, robust pooling layer to it. So for things like the pseudo-Huber and Huber penalty functions, there was essentially no overhead. So I think something like 4 hours on a 1080 Ti GPU to train for the ModelNet dataset. But for the non-convex penalty functions, so like truncated quadratic, you need to also initialize the solver so that it finds a good solution. So you could do that using ransack, or we just found the median and the mean and used those as initializations. So it took, that takes a little bit more time, but the bulk of the time is still just standard training of the network for these particular problems. And then the second part was, what is the size of the data or model that can be solved? I mean, I guess it depends what you would call adequate time. So in the work that I presented at this conference, we have 10,000 2D points and 10,000 3D points being fed into a solver. And so that's the sort of scale of thing that you can handle. But it really depends on what forward solver you have. So if you have an efficient forward solver, then you can typically put something like this in a end-to-end learning framework. But if you have a inefficient solver, or you're trying to solve something globally optimally, then it's typically less likely that you'd be able to do this in an end-to-end learning framework, because you want to be able to run this every single time you do a training iteration.
Thank you. I want to ask the next question. I'll give it to Brandon, then maybe also Stephen Gould. So, so this is a very new, relatively new field. So how do you see the future? So what do you think will come next?
Yeah, great question. It's something I felt a lot about, and I think there are a lot of kind of new sparks and directions to go. One of them would be if staying in the convex setting and looking at more applications of convex optimization problems, and looking at other like new modeling approaches of just using convex optimization and potentially scaling that, and kind of looking at new properties and kinds of other analytical tricks that you can do in that setting. So I think there's a lot of new convex optimization to be done in that space. Going a bit broader, and I think that there are a lot of interesting non-convex optimization problems as well that similar ideas can be applied to. So you can apply a lot of the same intuitions in non-convex settings as well. And I think there's this large class of problems that are somewhere in between convex and non-convex optimization problems that kind of give you this nice middle ground. And specifically, I think that a lot of like controls and reinforcement learning problems are very natural applications or kind of specific ideas of interesting non-convex optimization problems that have used this tooling. Because naturally, as again agents interacting with the world, a lot of like the reasoning problems that we solve can be expressed as like non-convex optimization problems, and potentially even, I guess, kind of going beyond this, I guess like this convex non-convex stuff, I was mostly thinking about continuous settings, but going beyond this, you can also imagine having kind of discrete or integral parts that are constraints of your optimization problem. And I think this captures a really large class of reasoning operations that kind of solve problems that we could have like that we would kind of like find useful and also find really hard to explicitly model with machine learning. So that's kind of the kind of like the tip of the iceberg answer for me on the kind of future directions in this space.
Steve, do you want to also?
Yes, I'll add. I'll add to that. I think. I mean, I think Brandon sort of covered it nicely. We also have. So it's now just another tool as well in practitioners' toolboxes, right? We have CVX PI Layers, which is a fantastic framework for practitioners to just start experimenting with some of these ideas and to see how they work in their particular applications. But the more sort of broadly, I think the whole conceptual idea of differential optimization layers and deep declarative networks goes back to what Stephen Diamond said earlier, in that you separate the declaration of your model and what it is that you want to do from the implementation, and the implementation is sort of hidden under the hood, and in fact can be swapped for particular implementations that meet your engineering requirements, whether that's an embedded system or a large scale system and so on. And so that gives you an understanding of what's happening within your deep learning model beyond what understanding we have today, where in a traditional deep learning setting, you have these very, very simple operations that allow us to learn from data and learn very efficiently, but we don't really have any guarantees or any deep understanding of what's going on within the network. Whereas from a conceptual perspective, when you start thinking about modeling your problem through these declarative layers, you get some guarantees and you get a better conceptual understanding of what it is that you're modeling. And I think that's beyond some of the stuff that Brandon talked about, that's one of the benefits of moving to these declarative layers. And I think in the future, we'll start to see some work in providing some theoretical guarantees on what it is that your network is learning by taking all of the literature that exists in optimization and analyzing that in the context of gluing these optimization problems together into an end-to-end learning model.
Thank you. So we have time for maybe 2 or 3 more questions, so feel free to pop them in the Q&A section below. In the previous Q&A session, we had several questions that were directed towards efficiency. So people were asking how efficient are those layers compared to the traditional ones. I guess, Stephen Diamond, do you want to comment on the efficiency?
Well, you can't really beat the traditional neural networks for efficiency, and so certainly there is a loss. And part of that is, as Akshay described, we haven't really, there's engineering work to be done that would go pretty far towards addressing that gap. For example, getting things on the GPU. I think one thing that would be interesting in terms of efficiency is early stopping for optimization problems, even for convex problems, right? If you're solving 1,000 of these problems, say a batch of 1,000, doesn't really seem like the right thing to solve them all to perfect optimality, right? That's probably not the right answer at least from a, if your goal is to get more efficiency out of this system. So there's probably a lot you could do there. So I guess my short answer is that the efficiency right now, it's certainly it's certainly going to be a lot slower to incorporate these things, unless they're in the sense that Dylan described. You have these particular implementations, in which case that may be just as good essentially. But for the CVX PI layers, it isn't really it's definitely slower than the neural network operations that people are used to, but hopefully not forever. I don't know if Akshay and Brandon want to.
Yeah. Anybody wants to also? Brandon?
Yeah, I do have just an anecdote to add on to that, or maybe even more of a negative result. I know I talked with this with Akshay and Shane and others before, but I was trying to combat this idea that CVX PI layers doesn't necessarily need to be slower than a neural network. And so I was essentially trying to train a neural network to predict the solution to CVX PI layers while kind of like avoiding kind of like the main computational overhead. So you would then have something that had the computational efficiency of a neural network, but it was backed by the like the convex optimization kind of like modeling formulation of CVX PI layers. And so I think that there's still kind of a good vision in this space of having kind of like fast approximations to convex optimization problems that kind of use some kind of learning to improve the solver itself. But in my negative result here, it was actually really hard to have a neural network learn the solution to convex optimization problems, because convex optimization problems express such a rich class of operations. So that's just a quick negative result that I don't usually talk about.
Thank you. Okay, so we have some more time for questions. So, we just got one. Another question to Dylan. In the lecture, you've mentioned that there are applications to neural ODEs. Could you provide some examples?
Yes. So the original neural ODE work, so Ricky Chen's work on neural ODEs, you can actually think of that as a declarative layer, or as solving an optimization problem where you have integral constraints. So they don't formulate it in this way, but it is an example of at least how we think of declarative layers, and they provide a solver for computing the gradient as well. So they've essentially separated the forward pass and the backward pass in a very similar fashion to how we envisage it. But it does mean that there might be more situations where you could use integral constraints in your optimizer, and so perhaps model some more physical phenomenon and dynamic systems type constraints.
Okay, thank you. Maybe we can use the last 5 minutes of the tutorial. So any of you that wants to say any like conclusion remarks, how do you see the future of the field, what you're working on right now, cool applications that you think nobody's working on? Let's start with Steve Gould.
All right, thanks. So yeah, I think there are a whole host of applications that are yet to be explored. It's like, as you mentioned earlier, this is still quite a new field, and the tool to really explore what you can do with these. I think certainly in the area of computer vision, and Dylan might talk a little bit more to this. We have many years, 50 years of research that has gone into particular problems and algorithms for solving those problems, and most of the time those are expressed as solutions to optimization problems, whether convex or non-convex. And so with this idea of deep declarative networks, we can start taking those algorithms and we can move them into the end-to-end learning world, where most of the time the problem is not about the formulation of how do you address the application, how do you solve the application, but it's more about how do you extract the features out of the images and out of the videos. And that's where traditional deep learning is very, very strong. If we can bolt on top of that the idea of embedded optimization, then we have a very, very powerful paradigm. I think, as I said a little bit earlier, the other area which is really useful is this conceptual area where we can start to think at a higher level of abstraction, and therefore get some guarantees out of what it is that the network is doing. So yeah, Brandon was sort of talking about his negative result on trying to get a neural network to learn the output of an optimization problem. There is this whole field of learning to learn and meta learning, but that field, even if you do get a network that you can show empirically to match or do very well on your test set, you don't have any guarantees about how that will perform on unseen data. Whereas with traditional optimization, you do have some guarantees, particularly if your problem is convex and you use a well-engineered convex solver.
Thank you, Steve. Dylan, do you want to go next?
Sure. So I think for me, the future in the computer vision setting, at least, is looking at situations where you have real hard constraints. So Brandon talked in his presentation about how useful this is in control. But I think you get many similar situations in computer vision tasks. So for example, you have real hard constraints when you're modeling a human pose, because you don't want people's arms to go through walls or penetrate into mugs of coffee and that sort of thing. And on another area, I think it gives you an ability to use some like non-differentiable algorithms in a way that you wouldn't normally be able to use in a network. So in the camera pose estimation work that I presented at this conference, I'm using Ransack to obtain an initial estimate to get a good solution to the objective function. And I think just being able to use these sort of well-loved algorithms inside a network is quite exciting. So I think exploiting, as Steve said, exploiting the many decades of algorithm development in computer vision, many of which are quite efficient because they had to be back in the day. I think that's quite a useful way forward.
Thank you, Dylan. Stephen, Diamond?
Well, I think Akshay actually would be a good person to talk to, because I don't know, Akshay, maybe you could address this, because you've done the most work now on looking at the different applications of these CVX PI layers.
Sure, yeah, I'd be happy to talk about that for a little bit. So me and Shane Barrett, who was also a co-author on several of these papers, have been interested in like two big broad areas of applications, both of which were touched upon by these presentations. So control and structured prediction, and we're really excited about both of these areas for different reasons. For control, part of the reason we're excited about the future of convex optimization layers is that control has like a really rich history of using optimization problems for to control real things in the real world. So I mean, linear controllers and LQR, these are all examples of like optimization problems that have been solved and continue to be solved every day to control sort of vehicles and other things in the real world. And sort of we're excited about CVX PI Layers sort of bringing some of these classical methods sort of into modernity. And so like, whereas previously control engineers had to and still do tune the parameters in their optimization problems by hand, we're really excited by the prospect of being able to drop your convex optimization problem into PyTorch and then run like a pretty exhaustive simulation, and then automatically learn a good, reliable, stable controller for whatever problem you have at hand. So we're really excited to see how that's adopted by both practitioners and researchers in the community. And for structured prediction, similar to how others have said, convex optimization layers and optimization layers in general, we feel give you like a really, really natural way to specify and sort of encode like whatever priors you have about your output. Like if you know, for example, your output is a sorted vector or something, you can add like a QP layer at the end of your network, and you're guaranteed, you will always have a sorted output. And you don't have to, rely upon sort of heuristic ad hoc ways of like parameterizing your network that guarantee to sort of try to guarantee that you can get whatever structure you have at hand. So we're excited that by sort of the rich sort of modeling capabilities that these layers provide for learning applications. So yeah, and I think like at a higher level, which maybe for this audience it's not as big of a point, but I've noticed that when I talk to many people in machine learning, they've sort of traditionally thought of optimization as something you do and not something you use to model problems. And so Stephen, Brandon, and I were all sort of excited about how optimization can be used as a toolbox for specifying and declaring a problem that you want to solve, and then you don't have to think about how it's solved. And our solvers behind the scenes will do it automatically for you. So we're sort of excited about bringing this sort of dimension of optimization to the machine learning community.
Thank you. Brandon, do you want to say the final comment on that?
Yes, happy to. And I guess I already answered this question, the same question earlier too, when somebody asked me this. So I'll keep it a bit shorter this time. But I'm excited about all kinds of extensions of like as beyond the convex setting and into like classes of non-convex and potentially discrete valued or integral valued optimization problems. I think that the whole class of kind of like possible ways of reasoning that we can kind of incorporate into our models goes much more than is it just kind of convex optimization problems. All the convex optimization problems are a large class. So that's kind of what I've been interested in. And specifically, I've been thinking about some like optimal transport problems that involve reasoning about how you optimally move distributions between each other with kind of applications to time series alignments. And I've also been thinking about this in the control setting as usual. And I think while for all of the reasons Akshay mentioned in the convex setting, which I think is a really large class of control optimization problems, you can use differentiable controllers to like help stop fine tuning or help stop hands designing or hands kind of tuning the controllers and kind of add machine learning into control in like this really rich and like vibrant way. I think there's also a really large class of non-convex control optimization problems that are kind of on the frontier where it's even harder to kind of keep hand engineering the terms in the controller to kind of to get away without using the derivatives through the controller. So that's also another thing I've been really interested in lately. But yeah, it's a great class of problems, and thanks for your interest.
Okay, so it is time to wrap up. So I'll just conclude by saying that this session was recorded and it will be available on the ECCV website at a later stage. If you have any further questions, you can contact us via email, which is in the tutorial website, along with all of the other resources, the code, the videos that were used in this tutorial. I would like to thank all of the speakers again and co-organizers. So thanks everyone. And before we finish up, can you just not blink for a second so I can take a print screen? I've been trying to do that the entire session unsuccessfully. So, okay, ready, go. Okay, now we have a good one. Great. Yeah, so this concludes this Q&A session. And yeah, goodbye everyone. Thanks for coming.
Well, thanks, Yizhak. Yeah, for organizing.
We have a comment in the chat. Thanks to all speakers for the session. Okay. See you.
Great to meet you all.
Bye.
Bye.
Yeah.